to go through data and get specific aspects of those data based on whatever we want. We can also easily generate reports using databases on search information and in a specific format. This allows us to access certain pieces of information and present them in a certain way. We have ways to automatically support data validation and verification, which we'll go into a bit more in the next few slides. A database follows a standardized format. So one system will have to access a database using the same protocols that another system has to use, and therefore a database can be shared by multiple systems. And also we can store a greater number of records than in an Excel spreadsheet, for example, because the database is built to accommodate a large number of records. This meme right here, I guess maybe it's a meme. Chinese hackers, Indian databases. I kind of like, so just to give you a bit of context, maybe some of you guys have picked up on this, but like, I have an Indian name. My family is originally from India, but I grew up in the US. Anyways, I think that probably when I visited when I in like the 90s, this is probably what Indian quote unquote databases look like. But actually, India's made a lot of strides in digitizing, just in digitization in general, particularly involving government-related data, just all over society. They've made a lot of strides. However, I'm still sure in some school somewhere, this is what the database looks like. Okay, so we talked about data validation versus verification. This is one of the purposes of using a database. Now, data verification checks that the input matches expected values in a database. So for example, when we're logging into Facebook or Instagram, that's an example of data verification. We're putting in our login details and we're checking against the database to make sure that the email and password pair that we entered also exists in the database. Now, this is what a database is used for. Data validation actually does take place inside the database. And data validation means checking that input follows rules for the type of input entered. So for example, if we were entering a credit card number in a database, we can automatically check whether the data entered, well, basically, if we have a credit card number and we try to put that in a database, based on the rules that we've specified, it's going to check whether that credit card number is of a certain length, whether it contains integers, whether it follows the correct format. And that can kind of be automated in a database. Now, data verification, I don't really see that as being automated like within the database, but the database is definitely used for data verification. In tables in general, in databases in general, but specifically with regards to tables, we make use of a concept called entities. So an entity is a real-world object or person, and that's represented by a row in a database table. So if we go back here, right here, the entity we're representing is a movie. So we're representing a movie, we're representing movies in general. This table represents movie entities, let's say, and each one of these is an individual entity. I guess those terms are kind of used interchangeably, but this is an entity of stars, or of movie stars, and I guess this is an entity of movie characters. The point is, when we're talking about an entity, we're talking about what is represented by a table. So right here, if we're representing a person, then an individual, any row in this person's table is a person entity. Those entities have attributes which are represented in the table. Now, this may seem like kind of a trivial or kind of just like a useless concept, but when we're talking about tables on a kind of a broad level later on, especially when we're working with concepts like normalization, it does come in handy to know what an entity is. The entity is a person. We have multiple people in our person's table. So we're basically representing the entity of a person, and you can say each row in a database is a person entity. Now, one of the most fundamental concepts to databases and really just databases, I guess, is primary keys. Now, right here, this says customer's database, but I would say this really represents a customer's table. So remember, in a database, we have multiple tables, and in each table, we need to have a primary key, which is also called a surrogate key right here. Now, a primary key is a field, meaning a column, with values that are all different. They're all distinctive. So if you look right here, each one of these is a different value, and each one of these could be used to identify these people in this particular table. And primary keys are important because they are unique values that are used to identify any given row in a table. So they're used for identification, which means they have to be all different. Because if these are the same, for example, then it doesn't make sense, because when we go to access 8001, 00000 and customer ID, we're going to end up with 2 values instead of 1. So it's not uniquely identifying a particular row. Now, primary keys are a fundamental concept, and foreign keys are another fundamental concept. So right here, we kind of saw this set of tables before, but a foreign key is used to link up 2 tables. So right here, we have employee number, we have employee name, and we have department number. Department number is a foreign key. A foreign key basically just means it's a primary key from another table, but it's the primary key of another table, but located in a separate table. So right here, these are all primary keys in our employee table. So this is our department table, and for department number, we have foreign keys. Each one of these foreign keys are actually primary keys in the employee table. So for example, 101 is actually right here. And that gives us department name of HR and a location of Delhi. So foreign keys are used to connect records in one table to records in another table. And again, when we have a database with multiple tables, this is how things are generally going to work. They're all going to be connected to each other in some way or form, maybe through intermediary tables, but that's the way it works. So foreign keys and primary keys are 2 really important concepts. Primary keys are used to uniquely identify rows in every table. Foreign keys are used to connect one table to another. Now, when we're working with tables in a database, every field or every column is going to have a specific data type. So you may have text, which represents a string of values, character, which may represent one single, or actually, I guess text is just a string. Character may represent one single symbol, number, or letter. You may have a Boolean, which can be true or false, or yes or no. You may have integers, which are whole numbers, reals, which are decimals, or date times, which are a combination of a date and a time, or just a date and time. The reason I'm actually going over this is because you may have to identify what data type specific fields would have or would match up to, given some prompt or given some information about a set of data. So it's worth knowing these different data types and what they represent. A lot of them are actually quite similar to what you'd see in programming. Text is basically just a string. Real can be represented in multiple ways. It can be represented as real, I think, in Java. I think in Python we more commonly call it a double. Date time, that's not really like a data type in programming, but it's often used, like the date time format is often used in programming in general. Now, again, just to illustrate, if we were to actually start working with tables, what we'd have to do is we'd have to create a table. And this right here is SQL, which we're going to learn about in a second, and we're using it to create a table. And when we create that table, we're going to have to specify the fields and their data types, as well as possibly some additional characteristics. So right here, we've written a query using SQL, the language we use to interact with the database. And this creates a table with 4 fields for a name, age, address, and salary. And the name is going to have a text data type, age is going to have an int data type, address is going to be a series of characters, salary is going to have a real data type because it's going to be a decimal. Now, you will have to understand SQL on the exam. You're never going to have to write this code on the exam, but I just wanted to put this here so you have a more real-world understanding of what tables are and how this whole table database thing works. So generally, if you're writing code, we would connect to our companies.db database. We would send this query. That query would be executed on the database, and then we'd close our connection to the database. Now, there are other types of SQL commands that we can run or we can send to our database to get specific values from the tables within a database. Now, in the context of the IB exam, we're going to be sending queries to get data from individual specific tables. So right here, I'm going to break down these queries. These queries specifically, you're going to have to know how these work for the IB exam, and you may even have to write some. So one of the most common ways in which we can find or get values from a particular table is going to be using the select from format, the select from keywords. So right here, we're selecting a specific field from the table products. So this is our field, and this is our table. This means that our output is going to be all 5 of these things. So we're going to get Chase, Chang, aniseed syrup, Chef Anton's Cajun seasoning, Chef Anton's gumbo mix. On the other hand, right here, if we select the product name and the price from products, we're still working with the same table, but we're not only going to get all the product names, but we're also going to get all the prices. So we may get Chase 18, Chang 19, aniseed syrup 10, Chef Anton's Cajun seasoning 22, Chef Anton's gumbo mix 21.35. So that's how select and from works. We're selecting a field from a table. I don't know why my formatting went haywire here, but this is basically just representing the concept that I just went over. And these are generally just called select statements. Now there are a few other things we can do with select statements. So let's take a look at this one right here. We have a table name of products. So we're going to select product name, okay? So we're going to select everything in that field, the field product name, from the table of products according to some criteria. So where the price is greater than 20. So that means that we're going to, for all of those rows or records in our table, where the price is greater than 20, we're going to output the field, we're going to output the product name. So that means really the price here is greater than 20 and the price here is greater than 20. So we're just going to show this and this right here. On the other hand, right here, we have select star from products where supplier ID is not equal to 1. So when you do select star, that means we're selecting all the fields. So product ID, product name, supplier ID, category ID, unit, and price. But we're only going to show all 5 of those fields for every record where the supplier ID is not equal to 1. That's what this one here means, not equal. So that means for these 2 records, we're going to show everything. That's what the star means. So again, this is another select statement, but here we're using this where keyword right here in order to set some criteria for what's going to be displayed. Now, this is similar, but here we're checking for the existence of a specific string within a particular field. So we're going to select, so right here if we say select star from products, so we're actually going to display all of the fields from the table products where product name like A, so where there's A in the product name. So that's going to be this one, this one, this one, this one, and this one. So really we're going to display the whole table basically. Not very useful. Right here, we're going to select product name. So we're just going to display the product name field from the table products where product name has cha. That's what the like keyword does. That like is checking for a specific string. It can actually do more complex operations like looking for patterns, but in the context of the IB exam, this is mainly what you're going to see. So so these 2 have cha in them. So we're just going to display Chase and Chang. So we're just displaying product names where the product name contains cha. Now, when you look at some of what's going on in the IB exam, in terms of what types of questions you're asked to answer, you're going to see a distinction between simple and complex queries. Now, right here we have what we could consider a simple query. So select product name from products where price is greater than 20. That's simple. This is going to be complex just because we've integrated some Boolean operators like and, or, mainly and or, actually, the really big ones. So all of a sudden, once we start working with more than one criteria, that's where we're kind of entering the sort of realm of complex queries. Not that these are really scary in any way. It's a lot like working with if statements in programming. But just keep in mind that you might see the use of and or to sort of create more complex criteria and accordingly complex queries that you'll need to either understand or write on paper 2, option A. Here's a quick little cheat sheet for everything we went over. Again, this is mainly what you'll need to know for the IB exam. I'm going to include this on the study guide that I'll be posting online, and you can take notes on it from here. So now that we've kind of gone over the basics of databases, we're going to start getting into some more complex concepts. And the first one is a secondary key. So secondary keys, so of course we're going to have a primary key, or we should have a primary key in every table. But secondary keys are those values in a table that are also capable of functioning as a primary key. We're just not using them for that purpose. So we can also use an account number as a primary key, because all of these values, all of the account numbers are unique, and the same is true with email addresses. But they're not being used as a primary key, so for now they're just called secondary or alternate keys. The difference between a primary key and secondary key is, while they both uniquely identify records, primary keys cannot be null because they are essential to identifying records in a database. However, secondary keys can be null. Also, we can only have one primary key at a time, versus we can have multiple secondary key fields. So this is going to have a caveat in the slides coming up. The next term I want to go over is a candidate key. So a candidate key basically encompasses both primary and secondary keys. They can all identify unique records in a database. And I mean, this isn't really like a huge concept. You just need to know that both primary and secondary keys are also referred to as candidate keys. Now getting to composite primary keys. So if we have a table and one field is not enough to uniquely identify records, but two fields can do it together, they together can function as a primary key. So a name is not enough because multiple people can have the same name, and they often do in a class. But anyone having the same name and birthday as anyone else is extremely unlikely. So together, we could use both these fields as a composite primary key. And the usage of two fields to identify a specific record in a table is therefore referred to as the use of a composite primary key. We've gone over keys in general. And as I said before, we've gone over a lot of the fundamental concepts involving databases and tables. Now, when we're planning databases and we're getting into the nitty-gritty of actually working with or creating our own databases, we're going to represent them as database schema. So here we're going to have different tables. We're going to show how those tables are connected to each other via primary key and foreign key pairs, what their data types are, what the field names are, what the table names are, and we may even have the length of that specific field. So here that's going to be 100 characters, and here that's going to be 12 characters. So database schema is basically an overview of a database, and it's basically an organizational chart for a database. And we'll be referring to and looking at database schemas a lot in the coming slides. Here's an example of a larger scale database schema. So now let's get into what a relational database is. In short, this is basically what you've seen for basically everything before this in this video. It's just the term for a particular type of database that we just went over that uses columns for attributes, uses rows for records. One term that we didn't really talk about before is is tuples, and the fact that records are also referred to as tuples. And you will often see this term on the IB exam in place of records or rows. Tables are related to each other using foreign keys, and each table has a primary key. So we described a database at the beginning of this video, and that is a relational database. Now there are other types of databases, particularly object-oriented databases, which if you're doing HL, we'll talk about later on. Now, one hallmark of relational databases is the concept of referential integrity. Now, what this means is that every row has an identifier or a primary key, and that every value in a foreign column will be found in the primary key of the table from which it originated. So what that means is that basically right here, we've got a departments table and we've got a students table. This right here is a foreign key table, and this is a primary key table. Now, what referential integrity means is that all of these department IDs will be found in our department table. As we can see right here, the foreign key, so the ID of 6 is not in the department table, so we get an error, but the ID of 1 is in the department table, so that is valid, and that follows the principle of referential integrity. This ensures that relations between tables are consistent, so basically they are all connected in a logical manner. Now, when we're working with databases, the overarching piece of software that allows us to manipulate databases is called a DBMS, or a database management system. So these, in short, allow us to read, store, change, and extract data in a database or from a database. Some examples of DBMS systems you might have seen are SQLite, MySQL, or PostgreSQL. And here again, just as we were talking about before, we have examples. Well, this kind of shows what a DBMS is, but then we also have examples of other types of databases, including objects databases, which we'll see later on. Now, there are multiple components in a DBS, or a database management system. There's a data dictionary, which manages metadata. And this metadata controls how the database is structured. There's features for data safety, including allowing for backup and recovering a database that's gone down. And also checking for data integrity, which is a term we'll go over later. There's a query processor. This allows us to accept queries in SQL and then return the appropriate output or conduct the correct operation. We have a storage engine that is really what handles the create, read, update, and delete operations. So really just like, this is kind of the workhorse of the DBMS. A DBMS also allows for concurrency. So that means we can have multiple users accessing databases and making changes at the same time without kind of colliding with each other. And then finally, there are security features which enforce user access policies. And basically what that means is that we have features that allow us to control what users can access what part of the database and who can make changes to the database. Now, what we're going to do is we're going to go into some of the concepts presented here and that involve database management systems in a bit more detail. So the first one is a data dictionary. A data dictionary is also referred to as a metadata repository. So this is a file or set of files that stores information about the database and the tables inside. So this is information about the structure of the database itself and about the organization of the database itself, rather than data. Now, this will include at a minimum the names and descriptions of tables, the names of fields or columns, data types and lengths of fields, and the relationships between tables. So this data dictionary is what allows the data to be organized in a specific way with certain tables, relationships between those tables. Now this is an example of so right here we have data, so we just have a table in our database. Here we have our data dictionary, and right here you can just see there's a bunch of information about how this table right here should function. So we have our various fields, we have the data types for those fields, we have descriptions for those particular fields for a developer. Right here we also have length, so what's the maximum length of any information that's going to be put in those fields. So that's an example of metadata that would be characterized, would be used to specify the characteristics of a given table. Now the next concept the next sort of functionality that a DBMS allows is concurrency. Now concurrency is the process of managing simultaneous updates or transactions at the same time. As to what transactions are, we're going to go over that in the next slide, or in the next couple of slides. But regardless, concurrency means we can have multiple people accessing our database at the same time and making changes to the database, or even to the same row. Although, what concurrency does is it prevents access by more than one user to the same row record at a time. So for example, if you had two people who wanted to change the same row, it would basically force them to get into a queue. So the first person's change should be made, and then after all of those changes are made, then the second person would conduct operations on that row. Basically, it makes sure that one row isn't written by one user while at the same time it's being written by a different user, which would just be a mess. As I said before, it forces sequential updates. Now, I think this is probably the last concept that we're covering with regards to DBMSs, but the DBMS also allows us to secure our database. So we can specify access rights, which we talked about earlier. We can say what users are able to conduct what operations in the database. We can specify, or we can mandate that there are audit trails. So this is a record of any changes that are made to a database. So if someone messes with the database or does something that deletes a large portion of the database, we can see who did that. We have data locking, and data locking corresponds to concurrency. Now, this means that a row that's currently being changed is locked and cannot be accessed. So while that isn't like security in the traditional sense, this just means that data is being preserved, right? So it's not necessarily we're securing it from a bad actor, but we're just making sure that everything is the way it should be. And the same thing goes for validation. Validation just makes sure that new data follows the rules, so it makes sure that data follows the correct data type and length. And again, this isn't necessarily security from like a hacker, but just making sure that data is in the correct format. We can have encryption, which is encrypting data in a database. And then we can have backups so that if something goes wrong with the database or someone makes a change that they're not supposed to a database, we have an intact copy that we can kind of load up and use in place of the corrupted database. Now, the next concept I want to cover is database transactions. So basically what a transaction is, it's a group of tasks. In terms of programming, it's going to be a set of SQL statements that are executed in order, as if they were one command. Now, this works differently from a typical just database operation. So usually you just run a command and that change is immediately done. Now, what happens in a transaction is that we basically have a set of operations and we conduct all those operations. So basically we keep a record of everything that needs to be done for each of those operations. So for operation 1, we're going to go ahead and we're going to keep track of everything that needs to be done for this to take place, then for option 2, and then for the other operations we have, without actually making permanent changes to the database. So in some ways, you could say we're actually making temporary changes to the database. We're just kind of basically putting in all the pieces in order to be able to make a permanent change. But we don't actually make a change until we commit all of the operations or all the temporary sort of changes that we made or that we've planned. So for operation 1, we might make a list of things that need to happen, then for operation 2, and then for operation 3, and so forth. But those changes aren't actually going to be permanently made to the database until we commit them. So you can either think of this as sort of a plan for changes or even just temporary changes that are being made, but that are not permanent. So if all of these are done, so if we've attempted a temporary operation 1, we attempted a temporary operation 2, we've done all of those, and there are no errors, then we can commit those changes permanently. So basically, transactions allow us to conduct a set of tasks, but in a way that doesn't actually alter the database. So we're basically making either temporary changes or we're basically conducting operations on the database to see whether a task is possible or a set of tasks are possible without actually making permanent changes to this database. And once we've gone through and done that and there are no errors, then we can permanently commit our changes. And one of the advantages of transactions is that if anywhere here we do get an error, we can roll back any other temporary changes that have been made. It's like nothing ever happened, basically. Now, maybe that was a bit convoluted. I guess the best way to summarize this is these are all temporary changes, and nothing is really done until we actually commit those changes to our database, which makes them permanent. So this is kind of how it works. So we start in the active state and we start conducting our operations. So we'll have a partially committed state. That just means that we've basically temporarily done some things. But if there's failure, we go to a failed state and then we abort and then we just terminate all operations. However, if everything is successful, then we just commit our changes and we're good to go. Now, transactions are important because they follow a set of principles called ACID principles. And that's atomicity, which means all tasks in a transaction are performed or none. So remember, a transaction is a collection of tasks that are temporarily done before being committed. Now, basically, unless all these tasks are successful, we're not going to do any of them. Next is consistency. So this means that all data must be valid according to existing rules. They must follow the correct data type, the correct length, etc. Next, we have isolation. This means that no transactions are going to interfere with each other. So if we have multiple transactions running at the same time, they're not going to be really affecting each other. If anything, they're going to be conducted in sequence. So one transaction, then another transaction, then another transaction. But the point is, they're not going to run into each other while they're trying to commit their respective tasks or conduct their respective operations. And next, the last principle is durability. So once a transaction is complete, the change to the database is permanent, even in the case of system failure. So atomicity, did I say that right? Consistency, isolation, durability. Now you need to know what all of these are for the IB exam. So the purpose of a transaction is to make sure that there's never an incomplete set of changes, especially like while, and particularly to make sure that one set of changes doesn't collide with another set of changes. So really, at their heart, transactions are about making more complex changes to the database using multiple different SQL statements. And with transactions, we can make sure that two different sets of tasks don't run into each other, but also all tasks are committed or none. Also, whenever we make commitments or whenever we make changes to the database, yes, they are permanent, but we also log them. So we log every single change that's made, so that makes it really easy if we want to roll back changes that have been made. So transactions made basic changes made using transactions rather than just simple SQL statements or simple like operations are actually more convenient because if we want to change them, we have them logged and we can just roll them back really easily or revert them. Now, what we're going to do is we're going to go through a few sets of concepts that lead us to normalization. Now, normalization is sort of one of the biggest and most, I would say, complex concepts in option A. And so it's important to us to be able to understand certain language before we tackle that. The first is data integrity. Now, data integrity it's a very broad term, and it's used a lot in option A just to basically say that like the data should be like what the user means it to be. So we can say that it refers to three things: accuracy. So we have the correct data in our database. That data is retained and preserved. It isn't changed for any unnecessary reason. And also the relationships are retained and preserved. So everything is like as we've planned it. Completeness, so all necessary data is available. Again, there's no data that's being deleted for no reason. And validity, all data meets all predetermined rules. That could be for length, for data type, whatever. Here we have a great graphic that kind of talks about how we can preserve data integrity. So validating input, that leads to validity, that connects to validity. Moving duplicate data, which also connects to completeness. Like duplicate data is not really what we mean when we're talking about completeness because we just don't really need it. Access controls are necessary for preserving data integrity because you don't want, if someone who you don't want is accessing the database, they might violate the accuracy, completeness, or validity of the data. And that's audit trails also help in that, so we can see who's changing what. And backing up data is another way to preserve data integrity because if something goes wrong, for example, if we lose some data, we can back that data up and we can maintain the completeness of the data in our database. So you just need to know that data integrity just basically means that everything's good in the database. The next concept is going to be data redundancy, and this is a huge concept. So data redundancy is a situation where the same piece of data is stored in two or more different places. So for example, if we look at this table right here, we have this row. So we have a doctor ID, the corresponding doctor, and the room for that doctor. And that's 3 times in the database. We don't need to have it in the database that many times. We could just have a foreign key to a table with all the doctors, and that would be sufficient. So if we have the same piece of data replicated multiple different places, the same database or the same table, those are all examples of data redundancy, and they're not considered good practice in terms of making databases or in terms of building databases. And that's one of the things that normalization, the concept we're going to tackle next, seeks to resolve. Now, while data redundancy is something we're trying to get rid of in the following slides, there are both pros and cons. So obviously the cons are more storage space is required because you're just storing more information you just hands-on have more information. But another problem is data inconsistency. So if you have the same piece of data at multiple locations, it may get updated in one location but not in others, which can be really confusing for a software system, or just can be really confusing in general in a system. Of course, the pros, and this really depends on how you store your data and where you store it, even if you do have multiple copies of that data. You may have faster data access speeds because if you have your data in more locations, you don't have to go as far in order to be able to access it in a database or just in RAM in general. Also, if you have data in more places, if you lose data in one place, then you can just replace it from another location. But this all relies on you being able to keep track of that data and know exactly where it is at all times. So now let's get to normalization. So normalization is a process by which larger tables in a database are divided into smaller tables while ensuring data integrity, which we talked about before, and reducing data redundancy. So some things we want to get rid of are attributes with multiple values. So this right here is a great example of an attribute with multiple values, I guess, right here. I mean, this literally has a table inside of a table. Or even like, let's say we have a particular table, or we have a particular attribute, right? And we have an attribute for weather, okay? Then we have both temperature and we have the type of weather in the same field, in the same cell. That's an example of having multiple values in one attribute or one field. You don't want attributes that are repeating the same type of information. We don't want attributes that aren't really related to the information in the table. We just don't want redundant information, similar to what we saw in the last slide. And normalization is a process, again, by which we're dividing up our database in order to prevent these particular characteristics. Now, generally, you want to use normalization to reduce data redundancy, as we touched on before, to reduce table complexity. So if we have tables, so if you have a database divided into multiple smaller tables rather than one big table, then overall we're going to have less complex tables, and this makes insertion, updates, and deletes less error prone. And also, we also just want to make sure that data is stored logically, because this makes it easier for us to write SQL queries, but also for developers or anyone who's working with our database, it's just a lot easier to understand, which makes it less likely that they're going to either damage the database's data in some way or just do something they're not supposed to involving the database. Maybe just structure it in a way that's illogical or that doesn't help the system function more efficiently. Now, when talking about databases, there are three normal forms that we're going to refer to. So each of these represent a set of standards for normalization. We can consider the first normal form to be the most stringent, or to be the least stringent form of normalization, and the third normal form to be the most stringent. Now, the first normal form mandates that we eliminate duplicate columns and columns with multiple types of values. We also want to create separate tables for each group of related data with unique primary keys. Now, the problem with normal forms is that if you look online or you look in a textbook, there's kind of like, in some ways, they kind of explain normal forms. Like they distinguish between the first, second, and third normal forms in different ways. So for example, some sources will say that the first normal form mandates unique primary keys, while others will say that the second normal form mandates it. I think the IB exam actually had primary keys in the second normal form, but that doesn't matter as much, just because for us to even have second normal form, you need to meet all the requirements for the first normal form. So regardless of where you put it, you're going to have to be doing that anyways. Anyways, that's the first normal form. The second normal form, meet all the requirements for first normal form, and then eliminate partial dependency, which we're going to talk about in an example here. And in the third normal form, we need to meet all requirements for the second normal form, and we also need to eliminate transitive dependency, which is another term that we're going to go through in our examples. Now, what's important is that on the IB exam, you're going to have to take tables that are unnormalized and then put them into, for example, third normal form. And understanding these concepts is important, but you're just going to need a lot of practice. And it really comes down to kind of seeking out certain errors, like multiple types of value, or multiple types, or just multiple values in one field, and understanding how you can split up tables to get rid of those. Before we get to actually normalizing, let's look at some examples, particularly of 1NF, 2NF with partial dependency, and 3NF with transitive dependency. Okay, so remember, with first normal form, we don't want to have any duplicate columns. We don't really want to have any columns with multiple values. Just generally, we are trying to have unique columns with one piece of data and primary keys as well. You might as well go with that. So this is our first table, and immediately we can see that there is a problem right here with this particular field. The problem is that we have multiple values in this field. So we need to rectify that problem. There's really no other problem here with this table. So what we're going to do first is we're going to separate these values in one table. So we are going to create a new table. And this is just kind of an intermediary step. And you're not actually going to do this on the IB exam, but I'm just doing this to show you like how we get from non-normalized to first normalized form. So right here in this table, we're just going to repeat So we have Jeff right here. Jeff had a 3.9 and was majoring in economics and math. So now we're going to have two rows that reflect the information. So we've got Jeff, and we have one row for economics and one row for math. And similarly with Alice, who's majoring in math and physics, we have Alice and one row for math and one row for physics. But that's only the first step. Now, we don't really have a primary key here, right? Because we have student ID, but we have them repeated. So those don't really function as primary keys. So what we're going to do is we're going to split this up into two tables. We're going to have one table just with the student data, and that's this table. We're going to have another table that combines our student IDs with majors. So we're going to have each student ID next to its respective major, and then wherever we have multiple majors, we'll have a student ID. That corresponds to each one of those majors. However, again, we can't use this as a primary key because we have keys that are repeated. So we're just going to create a new primary key, and that's going to be a simple ID. This should be 1, 2, 3, 4. This should actually be 5, and this should be 6 right here. And that's basically getting to first normal form. We don't have anything that's repeated. We don't have any duplicate values. We have primary keys in all of our tables. And we basically had to create those two tables to rectify this problem right here. This right here would have had the problem of not having a primary key. I suppose we could have added another primary key, but I mean, I think that this is definitely a more efficient solution, because right here we're only repeating our student ID, versus here we're repeating all three of these attributes. So remember, the name of the game is to repeat as little as possible to eliminate redundancy. Now with second normal form, we have a bigger problem, and that is partial dependence. So what partial dependence is basically when any given field first of all, partial dependence occurs when we have a composite primary key, okay? So right here we have two primary keys. We have the employee ID and the field ID, which are both unique. Now, the problem here is that the employee name has nothing to do with the field ID. I mean, we do have employee ID and field ID, but employee name is really just directly tied to employee ID. And field name is really just directly connected to field ID. So this is an example of partial dependence, because field name doesn't really have a connection to the employee ID, and employee name doesn't really have a connection to the field ID. Those are just very separate things. So you could use an employee ID to get an employee name, but not a field name, and you could use a field ID to get a field name, but not an employee name. At least that's what we see from this table. Now there's a couple of ways to rectify this. There's really only one way, which is splitting it up into different tables. So we're going to have one table for the former primary keys. The employee ID and the field ID go together, so those are going to be one key. Then we're going to have two tables for the fields that were formerly dependent, or for the partially dependent fields. So employee name was dependent on employee ID, so that's going to be in one table. Field name was dependent on field ID, so that's going to be another table. Now, oftentimes, we're making an assertion that field name is not connected to employee ID in any way from looking at this table. That's what we see. Now, we're making a judgment call. And oftentimes when you are normalizing your databases, you're going to have to look at the context, and you're going to have to decide whether there is only partial dependence or full dependence and how that works. But here we're assuming there is partial dependence, probably to illustrate the concept. And this is how we rectify it. So third normal form basically encompasses the concept of transitive dependency. Now we can say right here that pass-fail is transitively dependent on total marks. And the reason for that is because this attribute right here depends wholly on this one right here, with really no connection to name or seat number. These have no real impact on what pass-fail is. And total marks obviously is going to depend on the primary key, which is going to be name. Well, actually, it's not going to be name in this case. It's going to be seat number. But pass-fail depends on total marks entirely and doesn't really have a connection to seat number. Again, this is taking context into account. And this is a problem in third normal form. So in order to do that, in order to sort of rectify that, what we're going to do is we're actually just going to create a separate table with total marks and pass-fail, like so. And we're going to have seat number, name, and total marks in one table. And this comes down to having logically organized tables. Right here, we can also use total marks as our primary key because all the values are unique. So that's basically third normal form. Now it's important to know what all of these concepts are, but when we actually get to normalizing these, the logic is going to look different. We're going to be using these concepts of transitive dependency and partial dependency, but it's really going to be more from the perspective of reducing repetition and logically organizing tables in as intuitive a way as possible. So that being said, let's move on to actual normalization in the IB context. Okay, so now let's take a look at how to actually normalize tables, which is one of the most common tasks on option A. Now, here we have a set of steps. I'm going to caution you by saying that when I solve these, I don't follow these steps in exactly the same order. These are all things that need to happen at some point. But I think it'll become more clear in the examples that I work through following this slide as to how I use these steps to approach these problems. So the first thing I would say is you need to split your big table that you're given into separate logical tables by entity. So for example, if you've got cars, mechanics, and mechanic shop, and you have attributes for all of those in the same table, you need to split it up. And in each one of those smaller tables, you need to include what data corresponds only to that given entity. So for example, what corresponds only to cars needs to go in one table. You need to get rid of any attributes with multiple values by creating new tables. So if a particular column, attribute, field has more than one value, that should just not be the case. You need to get rid of that by dividing up your table into multiple tables. Make sure that there are no attributes that are only dependent on one primary key, otherwise new table. That's partial dependence. Make sure no attributes are dependent on another attribute that is not the primary key, otherwise new table. That's transitive. That falls into 3F or 3NF. Make sure that all tables are linked via relationships. So every table does not need to be linked to every other table, but it needs to be linked to at least one other table to the primary key, foreign key relationship, because ultimately they are all in the same database, and we need to be able to access other values and other tables through whichever one table that we are starting with. And finally, you need to make sure that every table has a primary key. Now, we're going to go through 4 different examples. The reason for this is that I know that these steps may not have been the most intuitive. And honestly, with solving these questions for me, sometimes I just have to intuit my way around them. So I'm not necessarily following these exact steps. So I'm going to use the brute force approach to teaching and just try to solve as many examples as possible, walk through how I do them, and then just hope that you guys understand what to do. So let's get started. So right here, we've got our first table, and we actually need to put this into 3NF, so third normal form. Now, the first thing we're going to do is we're going to look at the different types of entities that we have. So obviously right here we've got product, we have salesperson, and we've got manager, okay? So when we write our answers to these questions, we're not going to be creating new tables. We're just going to be writing the tables we're just going to be writing the table names with their fields. So immediately I can say we're going to have a table called product. And that table is basically going to have a number. It's going to have a number. It's going to have a unit price. And that's going to have a product name for sure. Now, I'm not too sure about date and time because for each one of these products, it's weird because for each one of our salespeople, we have 2 dates and times. And the fact that there's multiple values in this column tells us that we're going to need to use this to split into a new table anyways. So I'm kind of going to leave that out. It just doesn't, I know we're going to have to do something to that column, so I'm just not going to touch it, and it's probably not going to be in the product table. Now we're going to leave this open-ended. I'm not going to close the brace here so that we can add or we can change other stuff later on. Now the next thing that we know we're going to need is a salesperson table. And we can just start off by saying, we'll just say salesperson, and we know in that one we're going to have a salesperson number and a name. And next we're going to have a manager table because we have like 2 manager attributes. We're going to have, we'll just say manager, and then manager number. Well, I'm just going to go ahead and erase that real quick because we're just going to have a number. Well, I just don't want to write that much actually. We're going to have a number and we're going to have a name. Okay, so now that we have this, what we want to do is we want to basically deal with what's remaining, which is the date and time um, column, which we haven't really figured out how to deal with. And in order for us to figure out how to deal with that, we need to look at how this fits into the rest of the table. So right here, basically we have a date and time for every single purchase. So someone buys this product, and that product is sold by a salesperson, and that sale by that salesperson takes place at a specific time. And we know all of these dates and times are different. So what we're going to do in order to split this date and time up, in order for us to have a table where each row has an individual date and time, we're just going to say we're going to create a new table called sales, because that's really what's represented by each one of these times. And that's going to have a product number. It's going to have a product number. That's going to have a salesperson number. So we'll say salesperson number. And that is going to also have our date and time. Let's say D and T. Okay. So we've kind of accounted for everything by this point. We have a product with a number, unit price, and product name. And this works because of the fact that like all of these different attributes depend primarily on a product. In this table, if we had all of these attributes, so product name, salesperson, manager, all in the same table, that would basically mean that would basically violate our rule of transitive dependence, because of the fact that, well, maybe not necessarily transitive, it would in some way transitive dependence, because we have all these different attributes that are dependent on other attributes that are not the primary key. Like manager name is dependent on manager number, salesperson name is dependent on salesperson number, and product number, and like we have all of these different things are only dependent on the product number and not the salesperson number or the manager number. So because of that, that's kind of why we divide these into all these tables. Now, what we need to do now is think about our primary keys. So it's pretty clear that in our product table, that the product number is going to be our primary key. And the reason for that is that every product number corresponds to something different. So like we don't really have the same product number for anything. So we have 440 as a saw, 35647 as a drill. So we can say that product number is unique and has something individual that corresponds to it. And that the same kind of goes true for unit price. Pretty much every product number has a unit price, or even if it has the same price as something else, it's at least distinguished by product number and product name, which could also make it a composite key if you really think about it. Although, let's see. No, yeah, I guess that could be. But anyways, next, with salesperson, we have a number and a name. There's no salesperson, like every single salesperson has a unique number. So that's going to be our primary key there. So we're just going to draw a star by primary keys. And every manager also has, every like single manager has a unique name. So like 16 is Benson and 45 is Rogers. So we're going to have a primary key there. Now with sales, we do have some product numbers. Do we have any product numbers and like salesperson numbers that overlap? Let's see. Let's just go down. Or that overlap or that correspond to different salespeople. So like, okay, we've got, which one of these is actually repeated? So we have 35647 right here, which corresponds to 234. And we have 35647 right here, which corresponds to 199. So what that's telling is that we basically do have, we could use the product number and salesperson number as a composite key. Let's go ahead and see if there's anything else, any other problems. So we have 32.4. Yeah, I think that would actually work. So this would actually be, that would be a composite key. But if you wanted to have, I guess the problem is that the date and time wouldn't necessarily correspond to the product number, but would more correspond to the salesperson number. Although actually that's dubious. I think that these together could be a composite key, and that would be correct. However, if we wanted to just make sure in this case, we could also add a sales, ID, which would actually ensure that we have a unique primary key for each value in our sales table. So again, when in doubt, like just create an ID. And what this is going to be is just going to be 1, 2, 3, 4, 5, each one of those corresponding to a unique sale. And that's basically how we normalize this. Like, I know maybe this didn't look exactly like this right here, but I just wanted to walk you through my thought process so that you had a good understanding of how you go through and do these kinds of problems. That being said, we're going to do 3 more. And if you guys get tired at any point, just go ahead and skip on. But it took me a while as a teacher to really understand like how this worked. Looking at previous exams and mark schemes, and looking online. So I just want to give you as many opportunities as possible to understand how this works. Yeah, and this is basically our answer right here. This, as you can see, all of this is the same. Right here, we just had we had sales instead of purchases, and we have purchase ID instead of sales ID. But regardless, this would still be correct. And notice we get 4 points for correct table, 4 points for correct primary key. Now this is our next example. So right here, I guess we have like courses that are being taken, and students that are taking them. So like immediately, we have a few things. First of all, we have a student. We have students. So that's going to be one of our tables. Okay. So I know we have students, and then we have subjects. And we know that we're probably going to need another subject table because there are, for example, multiple subjects associated with the same student, like Anster. And whenever that's the case, that means that we probably need another subject table. But what compounds that and makes that even more the case is that we also have exam grades. So you have exams that are associated with subjects that are also associated with students. And we could say that exam grades correspond to our subjects. Our exam grades are connected in some way to our subjects as well. So that being said, well, I think I'm gonna stick with student first, and then we'll go from there. So with student, I think we know that we can have ID, which will be a key, name and gender attached. And I know with grades for sure, because every grade is determined by a unique combination of a student ID, a subject. Because if you have the student ID, you have the name and gender. So we could say that every exam grade is going to be a combination of a student ID, and each of these are gonna have to have their own ID. Well, let's say first of all, each of those is going to be a combination of a student ID, a subject, and the grade itself. So in that case, like I would say that, yeah. Right here, the problem is that we can have multiple student IDs with in different subjects, and with different grades. But the fact that we can have multiple student IDs in the same table means that we probably also need a primary key for this. So we could just say exam grade ID. And there's something missing. You don't really have the subject here. And I think this is kind of a problem because we need students to be associated with subjects in some way, right? So we have exam grades where we're just showing like what the exam grade is, and we have students. There's no real association, like there's no really way to tell, like based on a student, what subject they are taking. So I would probably say that the best way to do this, actually, subject is kind of on itself. There's nothing else that really depends on subject, is there? So I think probably what I'd put right just here is I'm just going to put subject. Because subjects are kind of just on their own. So that means that every student is going to be, actually that's not going to work, right? Because students have multiple subjects. So I guess we're back to square one. So we've got a table with students, student ID, name and gender. We've got exam grades, student ID, subject grade, and exam grade ID. We do have subjects included in here. I just don't really see any reason why we need a table for subjects. There's no other information associated with subjects besides the exam grade. So I think that's it. Let's go ahead and see what the answers tell us. And I guess we're right. So you have student, and they called it subject student. And they call it subject student, but that was pretty much it. So yeah, I mean, I know I was kind of roundabout there, but I do feel like kind of explaining my like weird thought process is the best way to look at it. And I guess this one actually asked us to normalize to 2NF. But I think that the way that we did it there's not really any transitory, was it transitory? Transitive dependence anyways. So I'm pretty sure 3NF would look the same. Yeah, I can't think of any real examples here where something is dependent on one attribute, but not dependent on the ID, or whether there's something weird going on there. Okay. So, all right, let's move on. So right here, we clearly have a few entities. We have a truck, we have a driver, we have trailers. So let's start with the truck. So for truck, we're going to have an ID, and it looks like that's unique for every truck. We're going to have a make. We're going to have an energy source. For a driver, we're going to have a name and a telephone number, which seems to be unique for all of them and can therefore be used as a key for a driver. Next, we've got trailers, and it kind of looks like these trailers are all making different journeys. So basically, because we have coupled from, coupled to, we have dates. And so it seems like we've got a few things going on. So, I mean, I guess the other issue is also the fact that in trailer ID and in trailer space, we have multiple values in the same attribute, which is an immediate red flag. And those values also seem to go together. So like we have TR2 and 60, TR9 and 30, TR2 and 60. So we're kind of seeing some patterns here. So I kind of want to separate this. Well, so it seems like so if we look at trailers in general, if we look at our data for trailers, we've got a trailer ID, we have the space in that trailer, and then we have dates that correspond to that trailer ID and trailer space. But those dates can differ as well. So for here we have TR260, and then we have it 1118 to 18618. Then we have TR260 from 1818 to 311218. So I'm going to take it like, I think these dates involve journeys. So it seems like we've got like trailer attributes. So we have specific data like connected to trailers and specific data connected to the journeys of these trailers. And I think it's kind of clear because it seems like anytime a trailer ID is repeated, like TR2, they have the same trailer space. Also, if you look at, for example, TR9, that has a trailer space of 30, and right over here, and right over here, but they're on different dates as well. So we're just going to create a table called trailer, and we're going to say trailer ID, and we're going to say trailer space. And then we're going to get to journeys. So we'll create a table called journey. And each one of those journeys, I think, should have an ID. So we'll say journey ID, but it should also have a trailer ID because each one of these corresponds to a trailer ID. So we'll have ID, trailer ID. And then there's going to be a coupled from and a coupled to. So all of these have primary keys. So that's the primary key right there. That's the primary key right over here, right over here, right over here. And we've kind of resolved that issue where we have multiple values or multiple values for the same attribute. So let's look at the mark scheme. Let's see how we did. Okay, I think we did pretty good. Right here, they used the driver instead of the telephone number, which I guess you could have done like either one. Each truck had a truck ID. Okay, so this one seemed to be correct, and this one right here seemed to be correct. And I think we got this one as well. Except I guess we're missing the driver, aren't we? Let's go back right here. So yeah, on the truck we didn't have a driver, which is my mistake. So I think each of these should have a driver. So I guess each of these should have a driver right here, because every truck, I mean, does obviously have its own driver. And I guess that's why we don't want this to be our primary key as well. We want to change the name to our primary key. And then right here, we're going to have driver, a driver name, and we can just use the name. I know we can just use the name as a primary key, because if we look right here, all of them are significantly different, right? So that kind of solves that error that we had. And I think the other error that we had was right here for journey. They had truck ID instead of just a regular ID. And I think that makes sense. And the reason why is because clearly, like, every single one of these journeys corresponds, not every trailer doesn't necessarily correspond to a specific truck ID, because of the fact that, for example, we have TR9 right here and TR9 right here. Sorry, I accidentally erased that. We have TR9 right here, and we have TR9 right here. But it does seem like every single journey corresponds to a specific truck ID, because every single one of these is unique, right? So we all have unique dates, and they all correspond to a truck ID. So right here, we're going to have, well, I guess maybe I will just add it at the end right here. Let's leave that blank right there. I'll add this right here. So we'll have truck ID, and together, actually, these can form a composite primary key, because you're always going to have unique combinations about the trail ID and the truck ID. So I guess a little mistake there. Let's put stars right here. But overall, that's the logic of how we do this. So that being said, let's move on to our final example. And that's wine. So right here, we're just going to do what we basically did, where we look at like the different entities that we have. And right here, it seems that we obviously have wine. Okay, so you've got wine, and that wine seems to be attached to, well, okay, so we have wine, and then we also have a problem, right? Because our description has 3 different types of values, and in reality, for it to be normalized, there should only be 1 value per attribute. So I think we can conveniently say that every wine, well, okay, yeah, so we can conveniently say that every wine has a name. It has a, I mean, it comes from vineyard, right? So it has a vineyard. It has a year. I guess dry is like a flavor. Alcohol content, so we'll say AC. And with unit price, what we want to do is, so we obviously have wines, all right? And we have these that correspond to unit prices. But we want to consider this kind of carefully because we also have store IDs, okay? So multiple stores that are in some cases selling the same thing. So for example, Sauvignon Blanc with Stormy, that's from Stormy Bay, that is 2017 dry and 12%. We have, like, these rows are basically the same up until we get to store ID, where we have a store ID of 2 right here and a store ID of 1 right here, and then stock quantity, which is also different. So those are different for that one. However, the unit price is the same. Let's go see if there are any other examples like that. So yeah, I guess right here we have Shiraz down here. And it seems like everything is the same, including the unit price. And obviously the stores and the stock quantities are different. Okay, so I guess we can conveniently say that like the unit price is also something that can correspond to each particular wine. So name, vineyard, year, flavor, alcohol content, and unit price. And let's see, do we have, I mean, a lot of these have, some of these have different names, but like, or some of these have the same name. So you have Sauvignon Blanc right here, Sauvignon Blanc right here, but they have different characteristics. So they have, for example, this one is 2017 dry and 12%, and this one right here is dry and 13%. So I'm going to go off on a ledge, and I'm going to say that we also need an ID here as well for each of these combinations. Okay, so that's wine. And the next is going to be vineyard. It seems like right here, if you look at our store IDs, like for example, you have store ID 2 and 1, and they're both in the same vineyard. So I'm going to guess that store ID isn't something that is specifically tied to vineyard. So like the vineyard here is Storm Bay, but then right here we have a store ID of 1 that's tied to James Tree as well. So I don't think there's a relationship there, but they all like there does seem to be a relationship between Stormy Bay and region. So like everything that's Stormy Bay is in Gisborne, everything that's Pecan Block is in Gisborne, everything that's James Tree is in Hawke's Bay. So I think we can say like for vineyard we're going to have a table, and the relationship there is going to be between the vineyard, the vineyard name, and the region. And that's going to be a primary composite key because every single combination is unique. We have Stormy Bay Gisborne, James Tree Hawke's Bay, we have John Glad Gladstone, so I guess we don't really need to worry about keys much there. And next we're going to have store ID. So we need to deal with the stores. So I think with store, like the thing is with store ID, I'm trying to see like what the store ID is actually going to be tied to. So store ID 1, it seems like it's in Stormy Bay, but then we go to store ID 1 in James Tree, so it's not attached to the vineyard as we said. But it does seem like we have a relationship between wine, store IDs, and stock quantities. So I think what I want to do is I go to wine ID, And we're just going to create a store wine table. So we're going to have different store IDs. So yeah, store ID is going to be one of them. We're going to have store ID. We're going to have wine ID, and then we're going to have our stock quantity. And in this case, the combination of store ID and wine ID should be able to function as a primary key, because we don't really have a case in which we have the same wine and the same store. So even these two right here, so like our Sauvignon Blancs, they have all the same characteristics except for the store ID. So yeah, I think we've got these could just both function as primary keys. These could function as primary keys, and we're just gonna have an ID right there. I'm sure there's something that could function as a primary key right there, but I think we're gonna stick with that. And I think we've accounted for all the different attributes. Let's look at the mark scheme and see how we did. So yeah, I think we did pretty good. Wine ID, wine, vineyard. Okay, yeah, that's actually perfect. Awesome. So those are actually like 4 great examples of different types of normalization problems. And like my logic didn't exactly follow the steps that I gave you, but as you can kind of see, you really just need to reason through them. And like, for example, if you go back to the previous problem, the first thing was always separating it into entities, right? And then once we separated it into entities, then we had to make sure that we had unique combinations. Well, first of all, we need to make sure we had primary keys for each table, but we also need to make sure that we never had tables where a set of information was repeating. So every single table had only unique rows. And that's kind of resolving, like doing a little bit of like kind of negotiating between this attribute and that attribute. So I think a combination of dividing into entities and that uniqueness coupled with having to have a primary key on every single table is really what helps you solve these problems. So if I were to summarize, I would say then entities, unique rows of data, and then primary keys. And that will get you 90% of the way there. Okay, one last thing I do want to say is that basically all of these questions that we went through right here, I normalized them to normal form 3, or the third normal form. There may be some questions to ask you to normalize the second normal form, but basically if you normalize it to the third normal form, then that by definition means that you've already normalized it to the second normal form. So basically just doing what we did on any of these problems is most likely going to work for you. And I can't think of a situation which it wouldn't. And that's the caveat I want to leave you with. Now what we're going to do is we're going to go on to talking about the advantages of normalization. So we spent all this time working on normalizing databases, and now I want to talk specifically about why we would do that. So first, if you remember, like when we were normalizing, we were trying to make sure that in every single row and every single table, there was a unique row of information. That means that we're essentially eliminating as much redundancy as possible, which means that less data storage is required to store the information in our new, smaller databases. And that's probably one of the biggest advantages. The second is that data is more likely to be consistent. Consistent meaning it's not going to be outdated, or there's not going to be duplicate information where one piece of information has been updated and the other hasn't. So because there is less redundancy, that means that there isn't the same information scattered around different places in your database table. And therefore, there aren't all of those, and all those places don't need to be updated. So that means you're only going to have a specific piece of data once, most likely in your database, and that's all it needs to be updated. Next, we can also say that we would have increased data security. And this actually just really comes down to the redundancy question. We know where every piece of data is, and we know it's generally located only in one place. And knowing the location of those pieces of data make it easier to protect. So there's not going to be a piece of data somewhere we didn't know about that isn't adequately protected either by encryption or by access rights or whatever else. Next, Updates and complex operations can be conducted more quickly and efficiently due to table structure. So this has a lot to do with there being smaller tables and with information being easier to find. This directly leads to being able to write simpler queries, being able to find and conduct operations more quickly and in a more targeted way. And finally, the last advantage is the fact that tables are more logically organized. So a database is easier to understand. And this is important when you're working with multiple developers, or if you're trying to explain your database schema to a team of business analysts or a team of non-technical staff. Just having tables more logically organized makes a database overall easier to understand. And the easiest way to get to that level of logical organization is through the normalization process that we just went over. Now, one last sort of vaguely connected, well, it is connected, but one random sort of concept we need to talk about is anomalies. And anomalies are directly connected to the normalization done in the second normal form. So specifically in working with the second normal form, we want to make sure they're primary keys on every database and that we don't have any partial dependence. Now, if we don't normalize according to the second normal form, we have three possible anomalies, which are basically problems that can arise. The first is the insertion anomaly. This is when a row can't be inserted due to a missing foreign key. So you've got all the data, but you don't have the data for a foreign key that connects it to another table, and so you just can't insert that data. The second is deletion anomaly. So it's when you want to delete one attribute, or you want to delete one row, but all of the attributes for a specific entity are lost when you do that. And the second is the update anomaly, so when data is only partially updated in a database. And let's look at some examples to actually highlight what that is, because these are kind of like just the dictionary definitions, but I just want to show you in more depth what each of these anomalies means. So right here we have a database of teachers and the departments in which they work in, along with like their phone numbers. Now, an insertion anomaly in this case is connected to the fact that we can't add a new department without also adding a member of staff, right? And this isn't necessarily connected to foreign keys specifically, but if we go back to our definition, we basically say that we can't, basically an insertion anomaly is when a row cannot be inserted due to missing data or without some piece of data that may not otherwise be necessary. And here, there's literally no way for us to add a new department without adding a new teacher, even if we have no desire to add a new teacher to that department at all. I mean, not that we're going to have empty departments, but every time we want to create a new department, I don't know that it makes sense to add a new teacher, especially when we could be adding existing teachers. So that's an example of an insertion anomaly. I think it just kind of helps better understand what an insertion anomaly is. Just going to go ahead and check that. Now next, a deletion anomaly. So for example, if you want to delete Betty Flood from the table, if we delete that record with Betty Flood, then we're also getting rid of any information connected to the geography department. And part of the reason for this is because there's no separate table for geography, which we would probably create if we were doing normalization. And this is an example of a deletion anomaly. We really just want to delete Betty Flood, but in doing so, we also delete the entire geography department and any information associated with it, like the department ID or the phone number. And finally, the update anomaly is related to the fact that if the phone number for the English department changed to 307 instead of 301, we'd have to change it for 3 different records. So the English department right here, we've got 301 right here and 301 right here. So if we wanted to change the phone number, we'd have to change it not only here, but also right here. Versus if we had another table for phone numbers, which was connected to this table via a foreign key, then we would really just need to update it once in the table for phone numbers. And then that's what we would access when we try to access our foreign key in this column. So these explanations are maybe in the previous slide, maybe a bit theoretical, but I hope that these examples really made it clear what we're talking about when referring to each of these anomalies. And that is pretty relevant to option A because you will have questions where it sort of asks you to define what these anomalies are or to talk about where and how these could occur in a given table. Now, the next thing I want to talk about is database administrators. So basically, a database administrator is like that is a person, and that's database administration is basically a job. And the role of a database administrator is to ensure that that data in a database is performant, meaning we can efficiently access data. It's secure, meaning that only those who have specific access rights are able to access specific data, and recoverable. So if anything goes wrong, then if anything goes wrong with the database due to external factors, then we have a way to recover all of the data in that database. So to be more specific, the database administrator is responsible for updating the database, adding or updating new data, relations, fields, and tables. Now, they may not specifically be updating new data. This is usually up to whatever application uses that database, but they may create new relations, new fields, and new tables within the database. And if that's being done in an automated way, they're at least going to test and make sure that those relations, fields, and tables are functional and operate efficiently. The next role, as you said before, was in maintaining security. Now, maintaining security refers to accessing or assigning access levels and passwords to users, just making sure that certain users can only access certain parts of a database. Next, there's managing backup procedures. So this might be as simple as setting up a system that backs up the database every night at 12 p.m. So that if something were to go wrong in that time span, then there would be a relatively up-to-date database that we could just slide right in to continue to function within the system. Although I guess only backing up once a day is probably kind of a problem. Probably once every hour or even once every minute, depending on how many transactions there are. And then I guess this is very connected to establishing a recovery plan for a database in case of a disaster or malfunction. So the recovery plan might include just switching out the current database with the most recently backed up version. There needs to be a plan or protocol for that to happen, and that's the responsibility of the database administrator. Now, one thing that the database administrator has access to is commands in a database definition language. Now, when we looked at SQL commands before, those are mainly to, for example, they were to update specific values in a table or a database, to create new rows, to delete rows, to basically change the data itself. Now, DDL commands are things like create, alter, drop, truncate, and rename. These are all commands in SQL, the same language we use to update our tables or to add information, but they're generally only available to DBAs. And rather than directly affecting the data in the database, they allow us to define and modify the structure of the database itself, the structure and metadata of the database, allowing us to define what the database looks like and how it functions on a more fundamental level. And the database definition language is used to generate the data dictionary. Now, if you remember, the data dictionary was the set of metadata or the set of information that basically told us what tables will exist in the database, what data types the attributes in those tables will hold, and how different tables in the database are related to each other, among many other things. So to conclude, the database definition language allows us to generate a data dictionary, or allows us to use specific commands to modify or define the structure of a database and the tables within the database. It includes commands like this, which are part of SQL. Okay, so the next concept we're going to talk about is data modeling. Now, data modeling is the process of creating a visual representation of a whole or part of an information system. And what we're really talking about here is planning out what a database is going to look like and how information is going to be related to each other in a database-oriented system, or in just a system in general. In the context of computer science, it's obviously going to be a software system. And we do this so that all stakeholders, meaning programmers, anyone involved in business, pretty much anyone who's working on the system, has an understanding of how things work. Now, when we're doing data modeling, what we're going to illustrate at a minimum is going to be the type of data used, relationships between those types of data, how data is grouped and organized within the system, and then data attributes. So more or less, we're basically creating a database schema. Now, the three types of models we're going to look at are going to be conceptual, logical, and physical. And this is kind of going from just thinking about what entities we have to work with and how those are going to be related to each other, to actually just creating a schema with data types, relations, foreign keys, and the data types for the attributes. So let's go ahead and let's look at an example of what that looks like. So right here, I've got 3 pictures with terrible spelling but great illustrations. The first one is conceptual. So as you can see with conceptual right here, we basically just have our different entities, and we can just see how they're going to be related to each other. When we get to logical, not local, what we're looking at, what we have right here is we still have those 4 entities. Then we also have what attributes we're going to have, and maybe some foreign keys, like right here, in order to make it clear like what exactly that relationship is. And then we get to the physical data modeling, where we have pretty much the most data. We've got our data types. We have all of our attributes very clearly. We have the exact database names that we want to use, and we also have, I would probably say that the relationships as well are illustrated in maybe a more easier to understand way. So basically, in terms of sophistication, we're starting with conceptual, and then we're going to physical, where we basically just have a database schema. Now, some of the advantages of data modeling are kind of similar to what normalization, like kind of what the whole normalization is in many ways, except data modeling occurs in the planning stage, and normalization is actually a process, like an actual process, I don't want to say programming, but it's basically an operation that occurs or that's done in the database. Now, to go back to just really what data modeling accomplishes, it helps us avoid redundancy, a lack of integrity. So it helps us prevent situations where our data doesn't always fit the rules that we set for it. And then a lack of consistency. And this kind of goes back to redundancy. This means that we're not going to have different pieces of data in different places that aren't being updated. And once we've modeled the data, it makes it a lot easier for the database administrator or for a developer to actually create the database, to write the code in order to generate that database. And to kind of summarize, just a lack of modeling may lead to a structurally deficient database, and you might run into a lot of problems down the line that you didn't expect to run into. And at the end of the day, you may just have to make massive and really inconvenient changes to your database to kind of rectify a lack of data modeling, or to kind of deal with the consequences, rather, of a lack of data modeling. Now, one way to model data, particularly at the conceptual stage, is to use entity relationship diagrams, or ERDs in short. Now, there are many different ways to draw them. This method right here is the one I prefer, and this comes directly from the IB exam. So right here, we want to draw a diagram to illustrate the following situation. Each individual may only hold one driver's license. So there's one arrow between a license and individual and some helpful text. Each individual may own more than one vehicle. Hence, we have this arrow right here with multiple arrows pointing to vehicles. And each vehicle may be owned by one individual only. So right here, if we had multiple individuals holding multiple vehicles, we'd probably have multiple arrows as well. So that being said, let's look at an example just to give you a better idea of like how this works and how you draw these diagrams. So right here it says taxonomy is the part of science that focuses on naming and classifying or grouping organisms. You can definitely trust the IB staff to come up with an example like this. Swedish naturalist Carl Linnaeus developed the current hierarchical classification system of taxonomic classification in the 1700s. The classification is hierarchical, so one class has many orders, and one order has many families. So birds can be classified under the Linnaean hierarchical taxonomy as aves. In one system of classification, aves has 23 orders, one of which is the order of Cerconiformes, which holds 6 families within it. Oh my god. Construct an entity relationship diagram that shows the relationship between the class, order, and family. So this right here doesn't really matter. I mean, I guess it's just an example. What you need to pay attention to is one class has many orders. So we're just going to draw a box. We'll just say one class has many orders, and one order has many families. Or I guess rather than orders, we can just say order right there. And honestly, I would probably just write here has many, just to make it like really clear what the relationship is. But that'd be a valid entity relationship diagram. And what we're going to do is we're going to look at the mark scheme, which I think has another type of entity relationship diagram. And so right here it says award a 1 for each correct relationship with labels. Award 1 for a top-down diagram showing the relationships. Basically, you have to illustrate this. And if we look at this, this basically says class. So one class contains n. N could be any number, right? So that could be many. So one class contains an n number of orders. And then we can say that one order contains n families. So this looks different from the ERD diagram we just drew, but it's just as valid, and it illustrates the concepts presented in a perfectly normal way. I would say the one thing is just like, don't get tripped up on this like ridiculously like complex, not complex, but I would say pretentious question. All right. I know there's like a lot of big words here and it just seems super complicated, but this is just a classic reading comprehension exercise. And you just need to drill down, and it's this you're looking for. This is the relationship right here that you're looking for. So now what we're going to do is we're going to take a look at the HL curriculum. Now the HL curriculum, luckily enough, doesn't really involve the same level of, I don't want to say problem solving, but we don't have complex problems like with normalization or even ERD. A lot of it's just memorizing a bunch of disparate facts. So that being said, let's go ahead and get started. So the first topic we're going to cover is object-oriented databases. Now, these are another type of database similar to relational databases, except here, data is stored as an object. Now, an object is basically just a construct. So it's basically a group of data and functions that can be used to access or manipulate that data all in one self-contained unit. Now, this concept of objects comes directly from object-oriented programming. But the point is there's really no tables, there's no rows, there's no columns. Basically, every piece of data is going to be an object, and that object we're going to have information that corresponds to that given entity. So I guess, for example, if we're trying to store data on, let's say, students, okay? So if you have students, we'll have their current grade, obviously their name, their ID, and then attach this object. We may also have some other functions like get final grade or something like that. I guess for that we'd also have to have a final grade attribute. The point is that we're going to have data and functionality combined into one package. And so basically, if we're storing students, we're going to have a bunch of different objects stored in memory or stored in our hard drive. Each one of those would correspond to a specific student. And those could also be related to other types of objects. So for example, we could have a student object related to a classroom object, and so forth. Except it's going to be related to one specific classroom project, or one specific class. Sorry, I didn't mean to say classroom project. I meant to say one specific class object. So a group of students may be related to one class object, another group may be related to another class object, and so forth. Now, there's no SQL, and data is manipulated using these methods. And these methods are generally going to correspond to an object-oriented programming language like Java, C++, etc. Now, the format for each one of these objects that's going to be in an object-oriented database is called a class. This is the equivalent of a schema. I guess it would be like a table schema in relational databases, right? So basically, like a class is going to specify what data can be stored in the object, what data types is going to have, and any other aspects that kind of define what each object is going to look like. And moreover, we can actually combine classes. So if you have a class for students and we have a class for IB candidates, we can actually inherit. So we can inherit the functionality from students into IB candidates, and then we're going to have a class that encompasses both of their functionality. We could call it IB students. So not only can we just use classes to create objects, but we can combine classes so that we can then have more complex objects that combine the functionality of both of those classes or more than one class. That's called inheritance. When we do that, We can also we can also use a concept called encapsulation. We can use other object-oriented concepts to specify what functionality is going to be inherited from one class to the next. I'm going to kind of stop there with getting too far into objects or object orientation. That's just kind of a really high-level overview of what object-oriented databases are. This is very heavily related to object-oriented programming, and that by itself could take up a whole nother video. And in fact, that is actually the focus of topic D, which is why I don't understand why it's here at all. But anyways, you should know this. So we're going to go over some of the advantages and disadvantages of object-oriented databases over relational databases. The first is that we can store a larger number of data types in object-oriented databases or in objects than we can in tables in relational databases. So we can have text, numbers, pictures, audio, video, pretty much, whatever we want within reason. Whereas, as we saw earlier in the slideshow in the SL side, we have specific data types that we can use in relational databases. Moreover, when we have complex data structures and relationships, so when we're talking about, for example, a particular entity that might take like 4 or 5 tables to describe in a relational database, we can just do that in one object using a particular class. And therefore, we tend to get better performance, better overall database performance, meaning that we can access data more easily, more quickly, and more efficiently. Or we can access complex data or complex data structures more efficiently, quickly, and easily using object-oriented databases than relational databases. We also have the concept of reusability. So remember how we were talking about classes and how we can inherit functionality from one class into another to create a totally different object? Now, basically, when we create classes, we can use the code for these classes over and over again in different contexts so that we can easily define objects and create complex data structures a lot more quickly than we can in relational databases. So in relational databases, we would need to add columns, maybe split a table into different tables. We'd have to do a lot more legwork to create new and complex data structures in an existing database than with object-oriented databases. And finally, object-oriented databases tend to describe or represent real-world entities more accurately. Just because, for example, if we have a person, we can easily specify a bunch of attributes that correspond to that person. It could be like eye color, weight, like height, I suppose hair color. There's a bunch of different characteristics really easily. And then we can also have functions that allow us to take whatever characteristics are there and combine them to get some other insight or whatnot. So it tends to be the case that just objects in general are able to more flexibly be used to represent real-world entities than relational databases are, which are basically it's obviously not an Excel spreadsheet, but it's very much just you need to have these fixed sort of fields, and that's all you're going to use. Versus we could also inherit from other objects or other classes, and we can create something really complex using a combination of classes quite quickly. Now, there are also disadvantages to object-oriented databases. When we're just working with really simple data and relationships that aren't too complex, object-oriented databases actually tend to be less efficient than relational databases. Relational databases can also be simpler just because this whole row-column model is actually quite simple to wrap your head around. There's a lot of ways easier to understand than object-oriented programming, which can be difficult for particularly non-programmers to understand. Additionally, we have more tools for working with relational databases. There's just a larger community surrounding relational databases. So that means we have more options for using relational databases and kind of building on those. And standards and support for relational databases are more stable. So changes in a database are less likely to be required. This kind of goes back to the second point. We don't really need to we're not going to have any dramatic updates. And there's a lot of support for working with relational databases. So we kind of know what we're going to be working with when we start a project. And we don't really need to worry about having to change things later on to meet a changing standard or something that's different with the particular DBMS that we're using. Also, object-oriented databases are less secure. We don't have the sort of formal access rights capability or even backup or yeah, I guess it was even backup capability that we had that's built into our DBMS systems and with relational databases. Finally, like this is kind of the double-edged sword of object-oriented databases. Like they can be whatever you want. I mean, you can pretty much create anything, right? Like you can have multiple classes, you can have different attributes. You have a lot of flexibility. This also means that you don't really have a concrete data model in the same way that a relational database that has these rows and columns functions. So if you don't really have a universally agreed upon data model, you can just end up with a mess. So relational databases tend to be more rigid, but also more standardized and easy to understand. Now, the next concept we're going to talk about is a data warehouse. Now, a data warehouse is similar to a database, but operates on a much larger scale. And while it is still relational, it contains much larger quantities of data and is often used for large organizations and businesses for data mining and analysis. So data warehouse is a much larger version of a database. It's used by large organizations. It contains larger quantities of data. Its main function is to take data from a bunch of different sources, combine them using something called ETL, and then put them into a data storage repository called a data warehouse. This can then be analyzed to provide insight into that data, which can be useful for marketing, can be useful for any sort of, like, I guess, political campaigning, or fraud detection, or anything that requires very large data sets. Moreover, well, actually, let's just go ahead and look at some of the advantages so we can get a better idea of how this is, like, why we'd use this, but also like how this is different from databases. So when we have large amounts of data, we're going to have better performance than databases. The system is optimized for quick retrieval and efficient analysis of large amounts of data. Now, our system called ETL, which we're going to talk about more in the next few slides, is quite quick at consolidating data from multiple sources and transforming it into a standardized format for easy and quick querying. And this means that we can take data from a bunch of different places. So if we go back to our previous slide, that could be a CRM system, well, I guess an ERP system. I kind of forget what some of these acronyms are. These are basically different software systems, a billing system or just flat files. And we can take, so we have a bunch of software systems. We can feed them all into our ETL system, and that will take it and put everything into a standardized data format, which is easy for any organization to access all in one place, rather than having to individually go to these different systems, all with their own format for displaying and storing data. And we can do that pretty quickly. And I guess standardization of data goes along with that. An ETL system is constantly sort of analyzing, consolidating, and transforming this data, which is why we talked about timely access. Finally, we have access to historical data. So generally, a database is going to focus on the data that's being used day to day, and historical data is not as important. But the whole object of data warehousing and data warehouses is to store data from as far back as possible, so you can use that data to gain insights and make predictions about the future. Now, one of the big concepts we talked about was ETL, and this is the process from which multiple data from multiple sources is collected, processed, and sent to the data warehouse. And this is generally a software system in and of itself. And it has three parts: extraction. Extraction is when we're actually just getting data from those different software systems. And this could be structured data, so data that has a particular structure, or it's organized a certain way, or unstructured data, which is just maybe a bunch of numbers. And this whole process of importing data and just kind of bringing it to our ETL system, just kind of taking it in, like kind of sucking it in, that's extraction. Now, transformation is when we take all this data that we've gotten from these software systems, and then we standardize it. And then we make sure that it has an appropriate level of quality and accessibility. So some examples of what we would do in transformation would be deduplication, so removing duplicate data, cleansing, so removing inconsistent or missing values that would just kind of throw off any analysis, and standardizing, so making sure that all values follow the same rules, and additionally are also kind of in the same structure. And the final functionality of our ETL system would be loading. And this is when we actually take the data that we've extracted and we sort of cleaned up, and we transmit it to our data warehouse. That's sort of the middleman between these multiple software systems and our data warehouse. Now, finally, to get to the main differences between a data warehouse and a database. So the data warehouse, we have mainly historical data. With the database, we have current data or data that's relevant to the day-to-day operations of a software system. With the data warehouse, we're typically dealing with terabytes of data. The database, we're dealing with gigabytes of data. Although it could be larger, and we could have we could have multiple database systems working together. This isn't as relevant as you think. The data warehouse data is maintained over time. Timeliness is not as important because we don't have users continually accessing the database. We're mainly using it for data analysis every now and then. The database, however, data is up to date because, for example, if we're talking about the database for Instagram, then we're like continually hitting that database, trying to get data and updating data there. As I was saying, with a data warehouse, users mostly have read-only access versus with databases, they can both read and write to the database. So the writing part with a data warehouse is going to be done through ETL. We're not really going to have users reading, or we're not really going to have users writing to a data warehouse. Again, actually, this should be flipped right here. So really, a data warehouse is used for making decisions. A database is used for everyday transactions. A data warehouse is optimized for more complex queries across large sets of data, versus a database is actually going to be faster for simple queries, like create, read, update, and delete. So for example, if we're just creating an account on Facebook, a database is going to be an answer. But if we want to look at all the Facebook users and kind of divide them into specific groups based on their behavior, then we're going to want to use a data warehouse. And finally, with the data warehouse, we're dealing with a relatively small number of users. We have more data, but we have fewer users who are accessing it to analyze it. And with a database, we're generally going to have more users. Again, think about a system like Instagram or Facebook or something like that. Now, the main thing we're going to do using a data warehouse is going to be something called data mining. And data mining is kind of a nebulous term. It really just refers to just analyzing a bunch of data to find patterns or relationships within that data. And we're going to look at 5 different data mining methods that you should be aware of. Now, the pros and cons of data mining are that it helps us understand behaviors, trends, or hidden patterns. We can detect fraud or risk. And generally, data mining operations, like the 5 that we just kind of mentioned, help analyze large amounts of data very quickly, more quickly than you just trying to use an Excel spreadsheet for whatever reason. The cons are the insights gleaned through data mining use personal information and can reveal insights that might compromise privacy or anonymity. Data mining can be very, very expensive due to the amount of just like computing power and data that's required to really do data mining. That kind of gets to the point where, that kind of gets to the next aspect, which is that data mining requires large databases or large sets of data. And this can kind of storing, maintaining, and even paying for this amount of data can present its own problems. Now, the first type of data mining is cluster analysis. Now, cluster analysis basically looks at data and then puts it into groups. It doesn't make any it doesn't have any groups that it's trying to it doesn't have anything that's looking for. So it's unsupervised learning. So it's purely just getting a data set, and then based on the particular aspects of that data, which could, for example, be Netflix users or Tinder users, it puts them into groups. Now, as you can see right here, it uses unsupervised learning. So there's no prior input or training of this cluster analysis algorithm that's required. It's just doing its thing. If you haven't seen the paper 3 video yet, I'd kind of actually recommend that you do that, because this isn't normally the case, but a lot of the concepts in paper 3 actually match up with the HL concepts in option A. And again, this option A has been there for like the last 6 or 7 years and had the same concepts. So it's actually kind of just lucky that there is that overlap. Now, some usage examples include finding a demographic of customers with similar spending habits, and also finding viewers in Netflix with similar watching habits and recommending stuff to them. So cluster analysis, basically just divide our data our data points into groups. Okay, so the next concept or the next type of data mining that we're going to cover is called classification. Now, classification is kind of similar to cluster analysis, but we're using supervised learning. So basically what we're doing is we're getting some training data, and that data includes, the point of classification is to allow us to make a prediction of some factor based on given data. So if we look at this example right here, what we want to do is, based on some data about a professor, we want to predict whether they're tenured or not. Okay. So with classification, what we're going to do is we're going to get some training data, and that data includes both the data, the information of the professor, and then whether they're tenured or not. So we're going to train our algorithm using that data, and then our algorithm should be able to just only get the data on the professor and then predict whether they have been tenured or not, effectively classifying them into two groups, which is tenured and not tenured. So basically, new data is added to the model and compared against the predicted outcome based on the training data. The training data is kind of like teaching a student how to solve problems, and then we're going to give the student problems that they haven't seen before and see if they can solve them. That's classification. Again, something that we did cover in paper 3. So that, which actually I'd probably say my explanations in paper 3 are probably going to be better than this one, just because that was the focus there. And right here, I'm just trying to cover this in as concise a way as possible. That's classification. So if we're comparing cluster analysis and classification, cluster analysis uses unsupervised learning, while classification uses supervised learning. Cluster analysis, we're putting in data without any information attached to it, so it's unlabeled. Classification, we have information attached to it, and by information, I mean that we have those tenured. We have whether it's tenured or not, right? So we're telling the algorithm exactly what we wanted to predict, versus with cluster analysis, we're just giving a bunch of data and just seeing what it comes up with. And the third point kind of speaks to that. So with cluster analysis, we have no prior knowledge of relationships in the data. Classification, we understand the relationship in data. In fact, that's what we're asking the algorithm to exploit for us, right? We're asking it to glean the relationship between data and whether those professors are tenured or not, and then use that to make future predictions. And both of them output groups of data points. So cluster analysis just gives us a bunch of groups without telling us what the significance of those are. And with classification, we're basically taking the data and splitting it into multiple predetermined groups as kind of set forward in our training data. Now, the next step of data mining is association analysis. Now, with association analysis, we're breaking up data sets by variables. And we want to find relationships in data sets between those particular variables. So for example, right here, we have an association rules network, and this is basically what our output is from doing association. And right here, just looking at the data, we can say that someone who always plays football always plays basketball. And the strength of that association, of that relationship, is shown right here, right? So a lot of these aren't really that strong, except for the black one right here. So you can say that someone who plays baseball probably plays football as well, just based on the data that we have. So with association analysis, we are finding relationships between different variables, or if we're talking about in a database context, different fields. We're specifically looking for the dependency of one item on another, and this is going to be unsupervised learning. So we're giving all this data, but we're not actually telling the algorithm, we're not giving it any training data, so we're not telling it about previous relationships between particular factors. We're just giving it all of the data, so all of the data for those fields, and just seeing what it finds. Now, examples of using association analysis would be doctors seeing what symptoms often lead to what diseases, or retailers seeing what factors lead to purchases. So we might have data on the amount purchased, we might have complete data on a given customer, and we can kind of see if there's any association or what associations there are between specific variables and the amount or the type of product that a particular customer or customers have bought. Now, next we have link analysis. So link analysis I've actually seen most commonly in sort of a criminal or a national security type context. If you've seen movies before with webs of a bunch of terrorists who are all linked together somehow, that's link analysis. So link analysis establishes relationships between different entities in the same data set. And the algorithm begins by deciding what constitutes a link. So kind of decides like, okay, what constitutes a connection between any given entity? Like what is the commonality here that we can use to basically decide that there's a link, right? And then once it does that, it decides what entities meet the criteria for these links and which do not, and then also to what extent. So the links themselves are going to have weights on them to show, okay, this is a really strong link or this is not a very strong link. So basically every one of these are actually also these entities, we call them entities, right? But in like sort of the link analysis world, they're referred to as nodes. So we basically have data for each one of these nodes, and then we're analyzing to see like how they're connected, what constitutes a connection. And then once we've done that, once we've sort of figured out a set of connections between any given node, then we are trying to connect them and see like whether they meet the threshold for having like a sufficiently strong relationship. A great example is using cell phone data to determine the hierarchy in a criminal network. And sort of the last method that we're going to go through is deviation detection. This one's pretty easy. Basically it's unsupervised learning, but we basically analyze a bunch of data and we just see like what stands out. So we're looking for anomalous patterns or significant deviations from the norm. And like right here, for example, we have this graph. Russia's probably a great example. So right here for Russia, we have the percentage of votes for winner and voter turnout. I guess we have this like sort of outlier here for like a bunch of voters where there's 100% turnout, and every single one of those people, and like I guess maybe this is like by district, or I'm not really sure how this works, but wherever there's like a ton of turnout, they're all voting for the winner, right? Probably, I mean, they've been paid. I guess it's not only in Russia, but whatever. Anyways, the point of this graph is to show that we're specifically looking for anomalies, right? And that's kind of the point of deviation detection. And some examples of using this might be an unusual switch in pre-electoral voting opinions, or even just to kind of detect anomalies in voting data, or a sudden pro or anti-candidate sentiment in a particular state. So something that kind of is deviating from the norm, so that whoever's campaigning can kind of take a look at that and try to figure out what happened. Now, this is kind of like, we're kind of done with data mining at this point. And we have two little concepts that we're going to go over that are just kind of on their own weirdly, but still appear on the HL exam. And the first one is spatial databases. So spatial databases are similar. I mean, they are relational databases, but they're specifically like kind of databases that handle data related to locations, geometric figures, or space in some way. So that means they're going to hold points. They're going to hold the points or coordinates of particular polygons or 3D shapes, or they may be geographic coordinates as well. And we can use the data in a spatial database to model the structure of geometric or 3D objects, or something on a map, right? And this is an example of a spatial database because we have latitude and longitude in this particular database. Also, there's specific like RDBMS, relational database management systems, or specific types of database management systems that have functionality related to spatial sort of analysis. And these will have functions that specifically allow us to deal with like coordinates or groups of coordinates. And they may also be tailored in other ways to more optimally store like data that relates to space, geometry, or location. The last concept we're going to cover is just data segmentation, which is kind of like, it's kind of weird to throw this in here because it's a bit fluffy and I don't really see where it fits in, because it's like we're going from like machine learning to like just dividing data. But anyways, data segmentation is basically the process of just taking your data and then dividing it by certain parameters. Like, so for example, you might take the data on everyone who's bought stuff in your store and divide it by age to see what people from each age group are buying and which groups to target. So we might segment our data by demography, by like the aspects of people, by psychography, I don't really, I guess, by their psychology, by their behavior, so what they're doing, or by geography, where they're located. That one, I can't exactly remember what that is. And these right here are some of the things you can do with data segmentation. Create ideal buyer personas, improve your product, target your marketing to a specific group. You can also analyze your reviews. So you might analyze reviews based on demography, so based on their age group or where they're from, and you can use that again to more optimally target those customers. And data segmentation just doesn't apply to marketing; it can apply to all sorts of different use cases. But marketing, I think, is an ideal way to describe it. That being said, that is the end of option A. I will say this has been one of the more difficult videos that I have created just because of the extent and the complexity of some of the concepts we're dealing with. I hope you found value in it. There is a study guide in the description that you can purchase, which takes all this data and puts it into a pretty lean and easy to understand package. It's great for revising. It also goes to help support the channel and all the work that I'm doing. And furthermore, all I really want to say is if you like this video, please like it on YouTube, subscribe to my channel, and comment as well. I love hearing you guys' feedback. You can also join the Discord if you have any questions. Other than that, have a nice day.